Good morning, everybody. How are we doing? You guys walk out of here and just not think about this stuff anymore because that was better than having to think about
I
it?
talked about it.
You talked about it all day long? Okay, we definitely need help. Yeah, so that's fairly normal for any physics class to walk out of physics class never wanting to think about physics class again. But do realize that I am up here swinging a bat, and that bat is striking directly against all of your preconceived notions about how the universe works. And I'm not doing it because I like to see people suffer. I don't do it because it makes me seem extra smart or something like that. I'm doing it because this is the way the universe is. This fundamentally is our best understanding of how the universe is put together. This section on modern physics. Relativity is a part of it. And we're going to move into quantum mechanics and things are going to get even weirder. And we, as physicists, didn't choose this. I want you to understand that right now. This is not something we physicists would have chosen for ourselves. Physicists are fundamentally lazy people. If we can get it done quick and fast and pretend it's a simple harmonic oscillator, we'll just do that and be done with it, right? So what Einstein and others are doing with modern physics is they're really challenging our conceptions, challenging what we know, really asking deep, insightful questions into the nature of time and space. And these are the results. And I know it seems like, I don't know, black magic or weirdness or something that never is going to affect you. It affects you directly today. And maybe today we'll get into some of those pieces of evidence, but it's probably going to be next week. What I want to do is another example of dealing with time dilation. And then we're going to move into lengths and how space is affected by relative motion. And then we'll start talking maybe about more of these evidences. Kind of depends on how far we get today and how well you're doing with definitions of things. Because at a functional level, to be able to do relativity, at least the mathematics and make predictions, we need to rely, I think at first, because your brain again is kind of pushing back against a lot of these ideas. We have to rely on these definitions. So let's go back to time. Time is something that, I mean, maybe we should, at the very first day of Physics 2A, introduce you to how we measure time, but we don't, because we just want to say time, and we want to get into kinematics, and we want to, make you believe that you can do this stuff and all that kind of, right? But now I'm asking you to think about how time is measured, and this is very, very important for being able to figure out who's got proper time, who's got dilated time, what's going on, right? So at a very basic level, how do we measure time? In the language of relativity, last time we were talking about this, what do I need to be able to measure a time interval? Not just one event, I need two. There's two things, right, that are indicating when time has begun being measured and when time has stopped being measured. Personally, I kind of like to think of it as the starting and the stopping of a clock, just as something to keep in my head, but sometimes clocks aren't involved, sometimes it's heartbeats. There's things going on, things that are being counted, things that are being observed, that bookend our time measure, right? So in the case of this problem, right, we've got a heart rate going on, right? And so my events are the starting and stopping of like a minute here, right? There's like a minute has gone by and we've counted a certain number of beats within that time interval. So part of the difficulty in conceptualizing and applying what we know about relativity so far, we really only know one thing, right? What we know is that time dilates. I can't remember what symbol I'm using.
Do a knot.
I do a knot, can I use P today? Is the proper time, right? One of these is proper, one of them is dilated, right? And being able to nail that and figuring out who has proper time based on the event. So what is the definition of proper time? It has to do with two events, right? But what do those two events have to have in common? Same location in space according to that observer. I may have failed to tell you this, but look, for a physicist, an event has a very specific XYZ coordinate as well as a time coordinate, right? There's 4 pieces of information I can know about any event that's going on around me. I can measure where it is in space relative to me, and then there's also this time component as I watch time evolve and see things happen, right? But this event has specific place at specific time. And the first event we usually call time 0, right? Like where we start our clock and then something happens, right? And the question we want to answer when it comes to proper time is, are these events taking place, do they happen at the same location, according to that observer? So, usually there are 2 people seeing the same things but happening at different times and at different locations. This is exactly analogous to you driving your car along a road, right? And maybe watching something happen on the side of the road versus somebody who's standing there, right? Somebody standing, watching something happen, the chicken cross the road, right? We'll see events take place, but you will see those events as you drive by as happening in different places with respect to you, right? Because there's relative motion there. Like you might pass the chicken as it begins to cross the road, but you'll be way down the road when the chicken finally gets over here, and you'll say, well, the chicken's at 2 different places. Relativity requires you to get into the mindset and point of view of everybody in the problem. It's right there in the title. Everything is relative, and that means relative to the observers. So who are the two observers we have in this problem?
The astronaut.
So we have an astronaut, and who else? Earth observers. Scientists, mission control, whoever they are, right? Okay. Again, I like to just draw some pictures with this stuff, right? We got the people on Earth, right? And we have the astronaut. I don't know why my astronauts are always surfing on the outside of their spaceships, but they are, okay? So I've got Earth, I've got my astronaut, right? And this speed, this 0.65 c, relative to who? Who sees the 0.65 c speed? Earth is only half the answer. Both of them see it. You have to get out of the mindset that Earth is always standing still. It's not. I drew this, right, kind of from the point of view of people on Earth as this rocket ship goes by, right, okay, at 0.65 c. But relativity requires us to see it from all points of view. The other point of view of this problem would be the astronaut. What does the astronaut see? Okay, astronaut sees Earth also moving at 0.65 c, just in the opposite direction. They'll always agree on that, right? So relativity tells us that both of these points of view, both of these measurements are correct. Notice that we are sort of holding not so much a paradox, but we're holding opposites in our head now. The relative speed is 0.65 c, but we see different directions for this motion. But in general, if you ask a person, right, like, you know, is that person moving? Is the other person? As two, if your car is passing another, right? From your point of view, they're moving in the negative direction, but from their point of view, you're moving in the negative direction, right? We can hold that contradiction in our head because it makes a kind of sense because it's based on the person doing the measuring. Special relativity, the same kinds of relativistic arguments hold. It's just now we're required to grapple with the fact that time doesn't flow the same when you're seeing things that are moving relative to you. And since both of these observers see motion relative to themselves, they are both going to measure a dilation of time. But now we get into the problem, like what is being measured and how do I define events and how do I determine who has proper time and all that kind of stuff. So we got to identify this time measurement, which I already did, right? It's 55 beats per minute. So there's a minute interval that's taking place, okay? And who measures that? So usually when a time is given, somebody is doing a measurement. In this case, we know that this time interval is being measured by the Earth, right? It's a 1 minute time interval. Since they're doing the measuring, we have to think from their point of view. So from their point of view, which is them stationary and astronaut going by, do they measure the beginning and ending of that minute to happen at the same place? Be careful. Note that they are observing something, right? So does the observation of the beginning of the minute, the beginning of the 55 beats, and the ending of the minute, or the ending of the 55 beats, are those two things happening at the same place or in different places? The answer is different places. You said same. I love this. This is great. You're wrong, but you're good. Okay? Right? It's easy to fall into this idea of, person standing on Earth, not moving, hitting a clock. The observation is of an event. Astronaut's heart begins to beat, right? I am using a clock. I'm saying 1 minute, right? So I'm gonna time 1 minute, but I'm watching heartbeats as they go by me, right? The astronaut's in motion. So the thing that is being measured from the point of view of the people on Earth starts in one place, ends in a different place. And again, it can be very easy to think wrongly and say, oh, well, the person doing the observing is not moving, so therefore they have proper time. That's the wrong idea. That's why I don't want you to clue in to motion. I want you to think deeply about what's being measured, what's being observed. What are the events that determine this, right? The problem does not say a person in the Earth on the lab starts and stops a watch in their lab, okay? They're measuring something where they're seeing the astronaut here, then they're seeing the astronaut over there, and so therefore that means it needs to be what? Is that proper? No. That's going to be what? Dilated time.
In the question, Earth-based observers measure her heart rate.
Yes.
Her being the astronaut.
The astronaut on the, yeah.
Just clarify.
Yeah, it can get difficult sometimes to follow the its and the hers and the hims and the yes. And the thems and the aliens and the Captain Picards and whoever else ends up in your problem. Okay. All right. All right, so we've hopefully, I'm not expecting you to nail this right off the bat. And a word of warning I should have given you on Tuesday. Homework, you're going to do a homework problem, you're going to get a red box, you're going to look at it, and you're going to say, oh, I just got the proper time rock and flip the thing and get the green box. Do not be satisfied with getting the green box. Understand why you chose wrong, right? Because again, these problems mathematically are pretty easy and it's easy to fix. You just sort of swap, right, what you thought, and it can be easy to go, okay, fine, I got it, I'm moving on. Do not move on until you fundamentally understand why you missed it. And when you can't figure that out, email me, Discord, Grass, something. This one requires you to like really bounce ideas off of each other, really kind of argue. This one's really hard to argue with yourself. I mean, physicists have gotten to the point where I can sit there and argue with myself back and forth, okay? But when you're starting out in this stuff, having a sounding board, having somebody, not your dog, okay, to bounce this idea off of. I mean, you can talk to your dog all you want, I'm not gonna judge, but they're not gonna help you. Dogs can do quantum mechanics, they can't do relativity. Okay, so we know that this time that's been measured is 1 minute. What's something that we can always get, by the way? The little success that we're gonna celebrate no matter what's going on in the problem. What can we calculate? Gamma. We should do that. Let's calculate gamma. 1 over the square root of 1 minus 0.65 squared. What happened to all the c's? They cancel out, right? So whenever you have a speed that's a percentage of the speed of light, decimal speed of light, you just drop it into there and you're good. If they give you the speed in meters per second, then you have to put c squared in the denominator. When I did this, I got a gamma factor of 1.316. Again, that number has no units, it's the amount, it's like the magnitude of the dilation that's taking place. It's not 1, meaning no dilation, but it's also not 10, meaning a lot, right? So it's slight, 0.65 C, it's moving pretty fast, but not nearly like if it were going close to the speed of light. Okay, so I got my gamma factor. I'm pretty confident, right, that these Earth-based observers are measuring a dilated time for the events that they are observing. They're observing the astronaut's heartbeat, right, as it goes by. They've clocked a minute, but everything's happening in different places, right? Okay. So I'm gonna go for it and just try to see what happens here, okay? I'm doing part B first because part A is annoying and I just wanna get the answer and then I can tell you what part A is. So calculate the astronaut's heart rate. Okay, so that means the thing that we can calculate would be the proper time, right? So just solving that for proper time, that would be the dilated time over gamma, okay? So in solving for the proper time, this again, the Earth people are doing this, right? Okay? They're saying we've measured events in different places, the time for that must be stretched out or dilated. So this calculation is going to tell the Earth-based observers how much time went by for the astronaut. And it's going to be a different time. And so we can see it's going to be a smaller time, right? So it's the 1 minute of dilated time divided by 1.316, which gives me 0.76 minutes. So we can stop and check here because based on what we learned on Tuesday, we know that when an observer sees something going by, just like the light clocks, right? Alette holding her light clock on the car, right? And Christian, his, right? What happens when somebody sees a moving light clock? What's happening to that clock? It's running slow, right? So even though on Earth, we've measured a minute, right? The clocks on the astronaut spaceship, we would say are running slower. And is that what we got? Did we get less time? According to us Earth observers? Yes, that's what we got, right? So grounding this in the concept. Very, very important. Okay, so we want to know heart rate though. We want to know number of beats per time. We've counted 55 lub-dubs of an organ. What has to be the same between the two frames? Time can be different, space can be different, but there is something that needs to be the same. The number of heartbeats. The heartbeat can be faster or slower, but the fact that 55 heartbeats took place. We're arguing about time, we're not arguing about number of heartbeats. Okay? These are, again, direct observables. The laws of physics are the same in every inertial frame of reference, right? So the observers agree that 55 beats happened regardless. So if 55 beats happened, but the astronaut would have only experienced 3/4 of a minute, 0.76, then this heart rate would be 72 beats per minute. This happens. In the frame for the astronaut, they would measure a quote-unquote normal heart rate, okay? But Earth-based observers would see these astronauts aging slower. Their heart rates would be slower. Their digestive rates, their cellular metabolism, everything would get stretched out and slowed down. They would age less. Okay? Interestingly enough, okay, we can do. I did the argument through time because I wanted to show you. But the gamma factor can basically be multiplied against things to figure out what the new thing is. In other words, if you take 55 beats per minute and multiply it by gamma, you get 72. Right? So gamma, if gamma is 10, right, and the original heart rate was 55, okay, then we would know it would be 100 and whatever. I didn't do that right. 550? Don't have a heart rate of 550. Okay. I didn't correct my heart rate. So if a heart rate of 2, no, heart rate of, let's try whatever 10, normal heart rate is 60, right? So heart rate of 6, right, being observed, and a gamma factor of 10, right? You could find the actual heart rate as if they were sitting still in your lap. All right, so that answers part A, right? Okay, the heart rate will be less than 55 beats per minute. Okay, so what I'm going to do now, same sort of situation, only changing the question just slightly. Okay? So the observers on Earth find people in their lab and they measure a heart rate for the person in their lab. I want you to figure out, okay, so the gamma factor is the same here. We haven't changed the relative speed, okay? I want you to figure out what the astronaut measures the person in the lab's heart rate to be. And the way I want you to do this is I want you to argue with each other, right? I want you to talk it out with each other and see if you can't figure out who has proper time, who has dilated time, how that's going to change the heart rate in the observations. Talk about the event. Talk about who's looking at what. I want you to do that for like the next 4 minutes or so. Really get into this because it's going to expose some weakness and some strength.
I will talk. Okay, so.
Yeah, but the thing that she's observing is, so that's why she is
Yeah, she's seeing it, the quantum thing.
yeah.
And then math-wise, it's. So.
Yeah.
Switch it.
So I think it's gonna be because so for the astronaut, she's gonna be in a different
The measurement is with them, you're saying, right? And then the observer doesn't have a clock.
I really wish you guys could like hear yourself. I should really record my students every once in a while. Just play it back. You sound so smart. Proper time this and clocks that and measuring this and heart rate that. And this is you try not to sound like this outside of class, don't you? Because you don't want to be seen as no, I'm not like that at all.
Oh,
I'm
no,
recent.
I
Yeah, no, it's yeah, I get it, I understand. Alright, so does anybody disagree with what I've written on the screen? We know our gamma factor because we know our relative speed, right? We know we're still talking about a 1 minute time interval, whatever it is. And we do know that 60 beats are being observed, right? Okay, so the question comes down to, is that time proper or is it dilated? Put your hand in the air if you think it's proper. So the rest of you think it's dilated? The answer is that this is proper time. Okay, so those of you that are celebrating, go away, right? The rest of us, okay? The rest of us are going, what the heck happened? Okay. Who's doing the measuring? The original measurement is somebody in the lab is looking at another person in the lab have a heart rate of 60 beats per minute, right? So the original measurement takes place over a minute, they count 60 beats. Proper time is the time that is measured between events that happen where? At the same place. Is the person in the lab in a different place than the person in the lab observing them after 1 minute? No. And so the 60 beats per minute, that 1 minute time interval, is proper time. In other words, the person in the lab doing the observing and the person they observing are not moving relative to each other. In that frame of reference, they're together. So the beginning of the 60 beats per minute and the end, the heart rate is not going clear, hopefully. Okay? So that means that the people in the lab measured proper time this time. Okay. The astronaut, from the astronaut's point of view, what are they seeing? It's okay. What is the astronaut seeing? Everybody check. I now know 5 of you have exactly the same alarm tone. What does the astronaut see? What do they see? They're watching somebody in the lab's heart rate. But what do they see it doing? Moving, right? From the astronaut's point of view, they're standing still and the Earth is going places. So they're looking at somebody in the lab on Earth, go past them, right? And if they start counting 60 beats, they're gonna be in a different spot. And Mr. Balogh, you keep saying this thing about different places and events, it's confusing me. Can't I just say it's moving? No. Yes, I know that events that happen in different places mean that it moved. But if you just clue in on motion, you will fall into traps. Okay? You have to do the work to think about what's being measured, who's doing the measuring, what they're seeing, if there's a different point of view, all that kind of stuff. It's important, it's critical. Okay, so we know that this is proper time. Or you get 50-50 chance to get it right. Do you want 50-50 chance on your exam? Some of you were like, maybe. Okay, so we know this is proper time, which means we're going to solve for a dilated time. That's going to be 1.316 times 1 minute, or 1.316 minutes. So that's the time, right, that the astronaut would have made measurement for 60 beats. And so if I take 60 beats and I divide by 1.316 minutes, I get 46 beats per minute. And I stop and I think and I go, wait a second. The astronaut records a lower heart rate. What does that mean? It means that time slowed down, right? Would time, according to the astronaut, appear to slow down for people who are in the lab? Yes, why? They're moving fast, right? How can two observers, smart, intelligent, amazing, understand everything that's going on, how can two observers measure different things for the same observation? The answer is going to hurt your brain. It has something to do with an idea called simultaneity. So I'm going to show you a video. I'm just going to let the video play, and you might get overwhelmed about 1/4 into it. That's all right. Okay. And then I'm going to play it again, and I'm going to pause, and I'm going to do a director's commentary on it.
Consider two observers in relative motion. In this case, Albert and Henry, just for the sake of argument. At the exact place and time they pass each other, they observe a flash of light. A sphere of light expands outward from that point. Since each measures the speed of light relative to himself, each believes correctly that he is always at the center of that expanding sphere, even though they themselves move farther and farther apart. How can two people in different places both be at the center of the same sphere? To confirm his perception, each sets up light detectors an equal distance apart. However, while Albert's detectors register the light arriving simultaneously, he believes the light strikes Henry's detectors at two different times. Meanwhile, Henry sees the same thing in reverse. They agree on the speed of light, but they disagree on whether events happen simultaneously or at different times. This is not semantics, nor a petty debate. It means that time, as well as distance, has to be affected by motion.
All right. If you fell asleep, let's do it again. I want to point out that what we are talking about, and what I'm about to try to explain to you about simultaneity, is all a consequence of keeping the speed of light the same for all observers. Everybody agrees that the speed of light is the speed of light no matter what. Remember that second postulate of relativity? All right, so let's see here.
Consider two observers in relative motion.
Okay.
In this case, Albert and Henry, just for the sake of argument.
I've already told you, Albert Einstein and then Heinrich Lorentz, who was the German mathematician that came up with the mathematics of relativity. Lorentz did not believe, by the way, that the speed of light was the same for all observers. He was arguing from a different framework, but he turned out to be wrong. Mathematician.
At the exact place and time they pass each other, they observe a flash of light.
Okay, so what is the setup for like the event? What's being observed? A flash bulb, like just a flash of light. Light turns off, turns on, turns off, right? There's this flash, right? And then that wave, okay, that flash of light begins to expand outward. Why? Because that's what light and sound and everything that propagate, right? It just goes out in every dimension, right? Okay, so they, and very sort of specifically, this happens when both of the observers, right, say that they are at the same place along the horizontal axis, right? They're crossing each other, that's where the flash of light happens.
A sphere of light expands outward from that point. Since each measures the speed of light relative to himself, each believes correctly that he is always at the center of that expanding sphere.
Each believes what? Correctly. Why would they both be at the center of the same sphere? They were at the same location when the flash happened. The speed of light is the same for both of them, regardless of how fast they're passing each other. And so they will be correct. This is direct observation, okay? They will be correct that they are at the center of the sphere. Even though what is happening? They are moving apart from each other. That should make your brain go, huh?
Even though they themselves move farther and farther apart. How can two people in different places both be at the center of the same sphere?
This is why we get graduate degrees in this kind of stuff, right? Like this is the question. It's either complete garbage, right? Einstein just had one too many in college and his brain is broken now, okay? Or we need to figure out what the heck is going on. Something has changed about how we perceive space and time by following this second postulate. And now, all of this would mean nothing if it was just words, right? If this were a philosophical thing, I wouldn't even be talking to you. I would say it's all complete garbage and we would do something else. The only reason I'm here teaching you this stuff is because this is what happens. You just got to keep trusting me on that one until we get to the evidence.
To confirm his perception, each sets up light detectors an equal distance apart.
So what are they now doing because they are scientists? An experiment, right? So they are going to attempt to quantify their observations, right? Record the data, see what's going on. And the experiment that they set up relies only on one thing. The one thing they can both agree on, which is what? the speed of light, right? So they're setting up these detectors, and when they say equal distance apart from each other, they're right in between their two detectors, right? So if they send the light beam this way and send the light beam that way, it should take the same amount of time to get there.
However, while Albert's detectors register the light arriving simultaneously, he believes the light strikes Henry's detectors at 2 different times.
So I wish they would stop using the word believe. Why do Albert's detectors go off simultaneously? He's at the center of the sphere and he's equal distant from his sensors, and so that's the only way it could happen. Why does Albert measure Henry's detectors going off at different times? Henry is moving. And so Henry is going to like that back one is going to, right? The light's coming this way and the back one's moving this way. And so that one's going to hit first. Whereas the one in front is like trying to move away from that light pulse, right? Okay. And so Albert, recording simultaneous events in his frame of reference, would say that Henry's events are not simultaneous. They happen at different times. But
Meanwhile, Henry sees the same thing in reverse.
in other words, what does in reverse mean? Henry says, no, my detectors go off simultaneously, at the same time. But Albert, yours goes off at different times.
They agree on the speed of light, but they disagree on whether events happen simultaneously or at different times. This is not semantics, nor a petty debate.
What's semantics? What does that mean? The way you phrase things. Semantics is word choice, okay? And so what they're saying is this is not about like the words that we're choosing to describe what's going on here. The narrator also says this is not a petty debate. What would a petty debate be? Yeah, not important. Okay, arguing over which kind of French fry to get at Five Guys. Like, it might seem like the most important thing in the world, but it really isn't. Okay? Or maybe like a petty debate would be a debate over something that really doesn't matter. It's just fun maybe to argue about which French fry to have. This is not word choice. It's not, what we're describing doesn't come about because of how we're describing it. Nor is this an idea that's just a throwaway idea. The fact that two observers performing the same experiment record different results means that we don't understand the nature of time and space. If we keep the second postulate of special relativity, that the speed of light is the same for all observers regardless of how fast they are moving, then what follows is time must run slower. And events simultaneous to one person, happening at the same time for one person, will happen at different times for another observer. And maybe even out of order. Which then means that it's not just time that's affected by this. It's also space. And by space, I mean the measurement of lengths. What is this? It's a meter stick. Okay. How long is it? It's a meter. How do you know? It's a meter stick. Right? Okay. The length of something is much easier to determine. Measuring a length, right? If I want to measure the length of this, hold up my ruler, I'm done, right? Okay? This is often an easier idea to latch on to, and so I'm finally kind of really throwing you a lifeline here with length contraction. Not only are lengths easier for us to visualize about like how we measure lengths, okay? But length contraction, the relativistic effect on the measurement of length only depends on motion. So proper time and time, right, that got a little bit convoluted, and events and same place and all that kind of stuff. With length contraction, you can rely on, is it moving or not? The proper length of an object is defined as the length that object has when it is at rest. In other words, if an object isn't moving relative to you, what's its length? Oops, I snowballed you. It's proper. Is this moving relative to you? Yeah, no. So therefore, it has proper length. It is the length that it's supposed to be. If now I take this meter stick and I move it at a significant fraction of the speed of light past you, it will not have proper length. It will have contracted length. And for a length to be contracted, what does that word mean? Bigger or smaller? It means smaller. So whereas time dilates and the time between events gets bigger, lengths contract by the same factor. The contracted length is the proper length divided by the gamma factor. This contraction only happens along the axis of motion. So what would an astronaut riding in a spaceship look like, right, as they passed by us, right? We're watching the astronaut go by, right? Do we on Earth measure proper length or contracted length for the spaceship? How did you know it was contracted? Because it was moving. Isn't this nice now? Right, this is just nice, okay? So, if the spaceship were just not moving, let's back this up. Let's say my spaceship, I'm gonna do a cube, because it's just easier for me to draw, okay? So there's the spaceship, okay, and its velocity is 0. If its velocity is 0, we would measure its proper length, right? But if the spaceship is moving, right, at some speed, it's only the dimension along the axis of velocity that gets contracted. So the height of this spaceship would be exactly the same, but its width would get squished up. And it's squished by whatever the factor gamma is, right? If gamma is 10, it is 10 times shorter along that axis of relative motion. We only ever do one dimension in here, okay? Because quite frankly, in relativity, you can make anything one-dimensional, right? Like, if the spaceship is going from down there to up there, okay? You're like, oh, it's two-dimensional motion. No, it's not. Just turn your head. Now it's one-dimensional motion, okay? Like, relativity, I can make one dimension in a heartbeat, regardless of how crazy the trajectory. Well, because it's special relativity, all trajectories have to be straight, right? We can't accelerate anything. So it's always easy to make a dimension along a straight line. Okay, so just be aware, length contraction, it doesn't mean the whole spaceship gets tiny, right? It would stay, if I really wanted to slim down really fast, right? All I'd have to do is run really fast, because you would observe me as being thinner. Same height, but being thinner. If I want to get, well, you can't get taller, there's no length dilation, so I'm stuck. All right, so length contraction, I'm hoping your brain is going, oh, wait a second, I might understand this. Like Mr. Balogh said, if it's moving, it's shorter, great, okay? Just in case I didn't have a ruler or something, I brought that. Okay, so what I want to do is I want to do an example of actually length contraction and time dilation. But I also want to start presenting real-world experimental evidence for what is going on. And where I promise you we will get to the everyday, R-scale types of things that are going on. But we are going to start with things that we can measure that go really, really fast. And these are subatomic particles. Subatomic particles, in particular, a type of subatomic particle called a mu meson, is generated in the Earth's atmosphere when cosmic rays strike gas molecules in our atmosphere, and they produce this thing that is like a, kind of like a big, fat, heavy electron, okay? But it's moving very, very fast, very close to the speed of light. I'm going to show you an experiment that was done, and you'll probably be able to figure when this was done just by seeing the footage, okay? But I'm going to show you the original experiments that were conducted about the generation of mu mesons in the Earth's atmosphere and how this relates to relativity.
Well, we do have some clocks.
A quarter of a century ago, Dr. David Frisch of
It's been
MIT
a lot longer.
and Dr. James Smith of the University of Illinois filmed a classic experiment proving the reality of the relativistic time dilation. They did it by measuring the flux through the atmosphere of a radioactive subatomic particle called the mu meson. Created at the top of the Earth's atmosphere by cosmic rays from outer space, mu mesons zoom straight downward at nearly the speed of light. But laboratory experiments, such as the one done here by Smith, show that mu mesons disintegrate naturally after an average life of only 2/millionths of a second. That means that even going at near the speed of light, they shouldn't make it very far through the atmosphere before decaying. Or to put it differently, when Frisch and Smith observed 568 mu mesons in their detector at the top of Mount Washington, they calculate that only 27 per hour ought to make it to the base of the mountain. But when they cart their equipment down to sea level, they find almost as many mu mesons as they had at the top, 412 per hour.
412. Oh, feet back.
Of course, Frisch and Smith really aren't a bit surprised. The reason for the discrepancy is spelled out by the theory of relativity. Traveling at nearly the speed of light, the mu meson's internal clock runs slow so that, as viewed from Earth, they take much longer on the average than 2/millionths of a second to disintegrate. Or, to put it differently, as viewed from the frame of reference of the mu meson, the Earth's atmosphere, rushing upward at nearly the speed of light, is Lorentz contracted to such a degree that the particle can easily make it all the way to the ground in only 2/millionths of a second.
Okay. So what year was this experiment done? It was the 1950s. Yeah, okay. Bow ties were still cool. What was the experiment? What were they measuring? Mu mesons, but in particular, they were counting. What were they counting? Number per hour, right? Okay. But the measurement was taken at the top of a mountain. Why go to the top of a mountain? Closer to where they're being made, right? So mu mesons have very high speed, they don't last very long, we're like 2 millionths of a second, right? Okay. So they calculate that the higher up a mountain you go, the more you should run into, right? But down at sea level, right, the mu mesons don't have enough time to get down, okay, to sea level. And so according to classical calculations, regular everyday physics, there should have only been, 27 instead of 500, whatever. But when they came down, they measured almost as many, in the hundreds, right? There's attenuation because of the atmosphere, so it's not exactly the same number. But it's not a factor of 10 smaller, right? Okay, which is what they predicted. So the classical way of talking about what these mu mesons are doing is failing. So what we're going to try to do is explain how mu mesons can make it all the way to the bottom. Okay? So I don't want to use this picture. I want to use this picture. I don't want to use that picture. I'm going to make my own picture. That's my backup picture in case things go wrong. Let's do this. Okay. So let's get some data down. First of all, we need a mountain. Mine's a very tall, spiky mountain. My mountain is not moving relative to you. It's just a thin, tall mountain. And I'm going to say that my mountain is 5 kilometers tall. It's a pretty tall mountain, by the way. It's like 3.7 miles or something like that. Okay, 15,000 foot tall mountain. All right, a mu meson, when it's created, is moving at 99.5% the speed of light. Cosmic ray comes in, strikes the molecule, knocks this mu meson off. Mu meson zooming away at 0.995 C. Okay? When you can measure a mu meson sitting still, we call this the rest frame of the muon. The lifetime, the amount of time a mu meson is in existence is 2.2 times 10 to the minus 6 seconds. So in other words, if the mu meson were standing still, it was created just standing still, not moving at 99.5% speed of light, so like just in the lab, you measure this lifetime of 2.2 times 10, 2.2 millionths of a second. So these things like might as well not exist at all or something, right? It's just a really, really short lifetime. And prior to the 1940s and 50s, we couldn't measure things that quick, but now we can. All right, so that's the time that the mu meson exists. If you want to anthropomorphize it, it's how long it lives. Okay, so it's generated here. This is where it starts, and it moves down, right? Okay, and we're going to say that they go in all directions, but we'll just count the ones that are moving straight down the mountain. Okay. From our point of view here on Earth, watching this mu meson get created at the top of the mountain and come down, do we ever measure the proper time, the proper lifetime of a mu meson? No. Why? It's created and destroyed in 2 different places, right? It's made at the top, it's moved somewhere else. The events are make mu meson, end mu meson. Those are happening in different places. And so this time right here, the only way we can measure the proper lifetime of a mu meson is if it were sitting still. And this data, this 2.2 times 10 to the minus 6 seconds, that is the proper time for a new meson. So if we are watching this mu meson get formed in nature, in the atmosphere, and come screaming down, that means that we are seeing a dilated time. Well, let's calculate the gamma factor first. If we can do that. 1 over square root of 1 minus 0.995 squared got me a gamma factor of 10. All right, well that makes the math a little bit easy. That means from our point of view, measuring a dilated time, we would see 10 times 2.2 times 10 to the minus 6 seconds, which means 22 times 10 to the minus 6 seconds. So we are seeing mu mesons lasting longer than they should. A mu meson decays after 2.2 times 10 to the minus 6 seconds, but when it's moving at very close to the speed of light, it lasts longer. Time is dilated, according to us. And since it is dilated, and distance is equal to velocity times time, now taking advantage of the first postulate of special relativity, which is that the laws of physics are the same no matter what, as long as you're not accelerating anything, then that means that I should be able to calculate the time it takes for a mu meson to get from the top to the bottom of the mountain. The time is going to be equal to the distance divided by the speed. Well, the distance is 5,000 meters, 5 kilometers, right? The speed is 3 times 10 to the 8, not 3 times, that's the speed of light. 0.995 times 3 times 10 to the 8 meters per second. And when I put that in my calculator, I get 16.8 times 10 to the minus 6 seconds. So according to me, the observer on Earth, watching mu mesons get created and stream down the mountain, a mu meson needs 17 microseconds to make that journey. Do mu mesons live long enough to make that journey? According to time dilation, they do. When a mu meson is in the lab not moving, it only lasts for 2 microseconds. But when it's moving at close to at 99.5% the speed of light, it lasts for 22 microseconds. Is 22 microseconds enough time to travel 5,000 meters that only takes 17 microseconds? Yes. So correcting for the time dilation that happens for mu mesons explains why we would measure just as many mu mesons at the top and bottom of the mountain. But this is I was just finished teaching you about length contraction. Why are you talking about time again, Mr. Well, they're coupled together, first of all. But number 2, we can argue this from the point of view of length contraction. This 5 kilometer length, who's measuring that 5 kilometer length? We are. We're looking at the mountain and we go 5 kilometers. Proper or contracted? How do you know it's proper? The mountain is not moving. If mountains are moving, we have a different problem. Okay? So the mountain not moving relative to us means that we have measured a 5 kilometer length. So who's going to measure contracted length? It has to be a frame of reference that sees the mountain moving. What's the only other actor in our problem? The mu meson. From the mu meson's point of view, sitting there at rest, what is it seeing? It sees the rest of the universe moving past it at 99.5%. In other words, the mountain, right, is coming towards it. Or at least the sea level is coming towards it, right, as the mountain passes by. So the mountain does not appear to be 5 kilometers tall to the mu meson. In the mu meson's frame of reference, where again, the mu meson only lives for 2 microseconds. Okay? The mu meson does not see a 5 kilometer tall mountain. It sees a shorter mountain. It's got to be the same width. just shorter, okay? 10 times shorter, right? The gamma factor here, right? The length, contracted length is the proper length divided by gamma. Well, that's 5,000 meters divided by 10, which is 500 meters. So the mu meson doesn't see 5 kilometers, it only sees 500 meters. Well, how far can it travel in its lifetime? Well, the laws of physics are the same for all observers in inertial frames of reference. So the distance a mu meson can travel is 0.99, well, or it sees the rest of the universe travel, 0.995 times 3 times 10 to the 8, right? Times the, what am I doing here? Yeah, times its lifetime, 2.2. This is the most amount of time it has to be able to travel. If you calculate how far a mu meson sees the rest of the universe travel, it turns out to be 657 meters. So from creation to annihilation, the mu meson sees the universe move 656 meters. Is that enough room for a 500 meter mountain to be there? Yeah, absolutely. 500 is less than 657. So whether you look at it from the point of view of time, or you look at it from the point of view of length, the only way to satisfactorily describe why we would measure the same number of mu mesons at the top and bottom of the mountain is to make the relativistic corrections that allow for time dilation and length contraction. Notice that the person who measured proper length measured what kind of time? The Earth observer measuring 5 kilometers calculated a time that was dilated, right? A measurement of proper length ended up giving dilated time. And a measurement of proper time gave a contracted length. It's kind of like yin and yang, right? If we're talking about the same events and things that are going on, then an observer measuring proper length is going to measure dilated time and vice versa. Just remember the vice versa is proper time and contracted length, not dilated length. No such thing as dilated length. Time dilates, okay? Lengths contract. And by time being dilated or stretching out, that does mean that clocks run slower, right? That can be a little bit of a hard thing for your brain to really come to grips with. Length contraction, you're like, oh, okay, so I think again it's because we do a very poor job from kindergarten on teaching you the nature of time. Talk about it. Okay. I want to, I got a little bit. I'll leave you with this. I want to show you the effects of moving this fast. We cannot, as of yet, send humans this fast without severely hurting them, okay? So we can, though, simulate what it would look like to move towards things. So these simulations are going to have some cheats in them, but the cheats are not physics cheats. That we're cheating. If we approach the Eiffel Tower at half the speed of light, blink and you miss it, right? So what we're doing is we are playing around with the time here a little bit so that we can see what's going on. We can't run it in real time, right? So what I'm about to show you is a supercomputer simulation based on the calculations of what would happen to your perception of lengths as we approach the Eiffel Tower at half the speed of light. So far, nothing seems too out of the ordinary, right? We're going along the ground, we pass through the bottom of the Eiffel Tower, big whoop. But remember, half the speed of light, the gamma factor is still really close to 1. Not much is happening. And in fact, if I told you what to look for, then maybe you might have been able to see it. So it's really hard to see in that high speed light. But now we are going to go to 90% the speed of light. So gamma factor is hovering around like 1.7 or something like that, okay? So see if you can't catch some oddities now. Does anything look kind of weird? Oh. Ooh. Things have got a little bit kind of spready outy, kind of warpy-ish, right? Kind of benty-ish. Like a fisheye lens kind of effect, right? So the parts of the Eiffel Tower that are further away from you don't move as fast relative to the parts that are closer to you, right? There's just things that are far away that are moving fast seem to move slow and vice versa, right? Again, this calculation is taking all of that into account. But even at 90% the speed of light, it looked a little bit weird. Well, here's 99% the speed of light. Nah! So now we're seeing the back of the front legs and the back of the back legs before we see the top of the Eiffel Tower, which we have now passed through the Eiffel Tower and still see the top of the Eiffel Tower. Is this something that you would have predicted? No. This is weird, right? Moving fast by objects allows us to see the backs of those objects before we finish passing through them. It allows us to see the tops of objects when we normally would not be able to see those tops of objects. If you flew past Saturn at 99% the speed of light, this is what it would look like. We have passed Saturn already. But what we see does not match up with our classically, as soon as you pass a planet, it's in your rearview mirror, right? Can you imagine traffic laws if you were allowed to drive close to the speed of light? Right? Check your blind spot. I can see it for forever. Here is what happens as you speed up. So 50% the speed of light walking down the street. 66, 70, we're up to 75, 80%. See how it's starting to warp more? 90, 95, gonna get up to 99. We're gonna start seeing buildings that are a street over and their tops, and now we're slowing back down. This is not the physics that your great-grandparents created. This is not the physics that you have experienced for a semester and a half. This is entirely new territory, and we will delve more into it on Monday lab. Either B square or at least a very tall rectangle.